Good morning. In the last lecture, we had seen various type of digital voltmeters, various configurations in which digital voltmeters could be used. In this lecture, we'd look into digital multimeter circuits. That is, ways in which the digital voltmeter can be used for current measurement, for resistance measurement, and for others also. So before we delve into that, we will have a relook or have a more detailed look into some of those features that make the digital voltmeters advantageous over analog meters. And we had mentioned these in the last lecture itself. That is, they are these properties. They are it is the ability to have auto ranging, automatic polarity detection, and auto zeroing features in digital voltmeters. And when you mean by auto ranging, when you say auto ranging, what you mean is that the first of all, the voltmeter can be multi-range. The same instrument can be used to measure voltages of widely different ranges, and the appropriate range can be selected automatically. Okay, that is the auto range feature. Okay, so and you can have a circuit inbuilt into the digital voltmeter such that it can detect whether it's a positive voltage or a negative voltage that is getting into the circuit. And we have seen in the dual slope DVM that we need to start every measurement starting from 0, and so you can have a circuit that will reset it to 0 without an external trigger. So let's have a look at each of these features, each of the circuits, one by one. Okay, so one is the multi-range feature, which is also possible in analog meters also. Okay, and the circuitry is quite simple. That is, here we have configured in a manner such that let us say if the switch S1 is closed, then you have a 2 mega ohm resistance here. Okay, and that is being and so the V1 is 2 mega ohm, and that is passed through this buffer amplifier. Okay, and now if you change from S1 to S2, what is happening is that instead of a 2 mega ohm resistor, what you have is Vin is connected to a 600 ohm resistance, and Vout is connected through the buffer and a 1.4 mega ohm resistor here. So a part of Vin goes into a system. So basically you are using a voltage divider circuit, and the appropriate voltage, the output voltage, a scaled version of Vin is given into the buffer amplifier, and the appropriate reading can be scaled up depending upon whichever switch is being used here. Okay, and this feature is this sort of a attenuation and measurement is also possible in the multi-range voltmeters or multi-range ammeters that we had in analog meters. What distinguishes here is this feature is these two diodes. Okay, they are input protection diodes. So in the earlier case, if you use the meter in a wrong configuration, it will inevitably have led to the damage of the meter. However, in the case of a digital voltmeter, you can have an input protection circuit. So now whenever you have the voltage here, that is alpha times V in, okay, the proportion of V in that is coming in, if that is, let us say, if that is alpha V in is greater than plus Vz, okay, then this diode will be forward biased, so the further circuitry is protected. And similarly, even if alpha V in is less than minus Vz2, then also then the second diode gets activated, it will get forward biased. Then also what we would have is that the further circuitry is protected, and there is only, so the voltage here would be plus or minus Vz only, it doesn't go beyond that. Okay, and probably you can have a case where if it is showing plus or minus Vz, we can say there is an overload that can be detected. Okay, now regarding the auto ranging circuit that you can have in a digital voltmeter, the philosophy is that you have the multiple ranges in a manner that there is a small overlap between the different ranges. Okay, like here you have it from say 0, not even 0 volts here, let us say 0 volt to 199 millivolt. Okay, that is one range. The other range starts from 0.18 or 180 millivolt and goes to 1.999 volts. Okay, and so on. Okay, and the way it operates is that you select a particular range and see what is the reading, and what you need is that the reading that you get. So if you have a 3.5 digit display, that is a display that goes from 0000 to 1999, the first digit can only be 1, okay, or 0, it can't be anything other than 1 or 0. Okay, so in a 3.5 days display, you have this philosophy that you choose a range, and then in that range, if you see whether, let us say you're choosing this range, whether the reading 0200 is achieved at all. Okay, so if it is not achieved, then it is most probably it is less than this range. Okay, it is less than this reading, so it can go to the lower range. And if it doesn't satisfy, if it goes beyond 1999, then you shift to the higher range. Okay, and if it remains between, if the reading that you get is between 0 to 100 and 1999, that is the range that you want to take in. Okay, now what is the advantage? And anyway, there is an overlap between the range. Now let us take one or two cases and see how this works out. Let us say you want to measure, say, 1.5 volt. Okay, and in another case, so this is case A. In case B, what you want to measure is 0.19 volts. Okay, and or let us say this is 15 volts rather than 1.5 volts. Let's say it is 15 volts. Okay, so in the first case, you start from here. Okay, 15 volt is greater than 1.99 volts, so it will go to this range. Here you get the reading as 15.00 volts, and that is done. Okay, now in the second case, what you have here is that you again start from this range. Okay, however, what you are measuring is 0.19 volt, and the range that I have is 0.18 to 1999. So the reading that you probably would get is 0190. Okay, and so this is less than 200, so this will go to the lower range. Then the reading that you now get in a 4-digit display is 1 9, let us say it is 1902, say this is 0.1902 volt. So all the 4 digits are now displayed. So it will have 0.190 volt or 190.0 millivolt. That is a display that you will see. So what is happening here is that due to the auto ranging circuitry or auto ranging logic, you end up with using the best range for the display. Okay, and because of this overlap, it is possible to avoid hunting. So if it was like, if it was in a manner that I go from 0 to say 200 millivolt and the next range starts from 200 millivolts, so if the voltage is very close to this limit, then there will be a difficulty in choosing in choosing whichever is the range. So if there are really small errors in the measurement, can cause it to hunt between these two ranges perpetually, and you will never be able to get a range, get a proper reading at all. So to avoid that, to prevent this hunting, you have this overlap. Okay, and because of this overlap, what would happen is it will settle into a range more easily. Okay, now the polarity indication is quite a simple circuitry. So you have two um, comparators here, and if the voltage input is greater than 0, then you would see that the output X would be high and Y would be low, because in both cases you are comparing it with the ground. However, the comparators, the sign of the comparisons would be reversed. So similarly, so if Vn is greater than 0, you have X is high and Y is low, and Vn less than 0, I have X is low and Y is high. And depending upon the sign of X and Y, okay, you can decide the way the DVM has to work out. That is whether the ramp signals, if we are using a ramp DVM, then whether ramp signal should go up from 0 or go low from 0. Okay, that can be decided, and it also would give us an indication whether the sign of plus or sign of minus should be put in front of the display. Okay, so that is how the automatic polarity detection would. So moving further, the zero detection, the auto zeroing, is something that we had seen earlier also, as I had said earlier, in the dual slope digital voltmeter. Okay, now in this case, what you have is, instead, in addition to the input voltage and the reference voltage, you have a third position in which the switch can be put in, which is connected to the ground. So this would, after each measurement, when S3 is activated, S3 is closed, then after each measurement it is reset, and the output of this DVM would be at 0 volts now. Okay, so 0 volt is equal to 0 reading, that is being reset again and again. Okay, now as I said earlier, the digital voltmeter can be modified to measure other quantities like current, resistance, frequency, etc. Okay, frequency, time period, etc. Okay, and then can be used as a digital multimeter. So you, in a digital multimeter, you also have measurements of capacitance, circuits that measure capacitance also. Okay, however, in this lecture we would concentrate only on the extensions to current and resistance. that is as ammeter or as an ohmmeter. Okay, so similar to the analog meters, the primarily current sensing element, the digital multimeters are primarily voltage sensing elements and, voltage sensing instruments, and they can be modified into an ammeter or a ohmmeter by having appropriate circuit for current to voltage conversion or a resistance to voltage conversions. Okay, let's see the current to voltage converter. So you have a overload potential circuit here. Okay, and let us say when there is a current coming in, it passes through a bank of resistors, and so when you have a current I that goes through a resistance R, then the appropriate voltage of V is equal to IR, that is being measured by the digital voltmeter circuitry. Okay, now how does this work out in this case? So you have a bank of resistors here. Now you would see that the resistance value are tuned in a manner such that when this circuit is being added, this switch is being closed, then the voltage, so let us say V1, okay, would be I in into 0.1. Okay, and if this was open and this is closed, then the other choice V2 would be I in times 1, and it goes by a factor of 10 each time you change the switch. Now what does that say is that when you have a current of, let us say, 2 amp or a range of say 0.1 to 2 amp that is flowing in the circuit, okay, then what you see is that a voltage that produced, let us say there is a 2 amp current, then passing through this would give a voltage of 0.2 volts. Okay, and similarly when you decrease the current range, let us say there is a 200 milliamp current and it goes through this circuitry, then again you have a 0.2 volts. Okay, so the same range of voltage can be measured from the ADC, and depending upon the switch position, it can be figured out what is the range of current that has to be displayed. Okay, and the shunt resistance are chosen in a manner such that Vmax, the max voltage, is the same for all the selections that we have seen, as you have seen in the example. Okay, now there is also one more way to measure, so without actually going through the conversion of the current to voltage, because basically in the digital digital voltmeter or in the digital meters, what we are basically measuring is the number of pulses. Okay, or so you are measuring either the time period or the frequency. Okay, so basically you're measuring the number of pulses. So you can say what is the time take, what is the number of clock pulses that pass when an n number of pulses are being measured, or how many number of pulses can be counted in a fixed time period. So let me again reiterate, you can do two things. One is that given some t, how many number of pulses are being pass or happen within that time period t, or given n, what is the time, what is the number of clock pulses that pass in a time that takes for n signal pulses to happen. Okay, these two things can be done, and basically in both of these cases you are indirectly measuring the frequency of the signal, some frequency of the signal. Now if we can convert this current or even the voltage into an equivalent frequency signal, or into a signal of some comparable frequency, then that measuring that frequency can indicate whatever is the current. Okay, so in this case what you have here is an integrator. Okay, and that integrator is linked to a comparator and a pulse generator. So what this happens is that there is an integrator that goes up, and it is compared with some reference. Okay, here it is given as minus V reference. So anyway, it's compared with that reference, so it has to go down in this case. So let's put it in this manner. So you have minus V reference here. So this goes from 0. Okay, and depending upon the magnitude of the current, okay, the slope of this signal this ramp signal depends upon the magnitude of the current that is being supplied. Okay, and once V reference is reached, this resets. Okay, and that causes a pulse. Okay, and then again this happens, and this things goes on. And so if you count the number of pulses, not the number of pulses, so if you count the time period, so now what is happening is that the capacitor charge rate is proportional to the input current IN, and the frequency of this pulse that is produced is proportional to the current IN, because as if IN is larger, this slope will be larger, and so it will appear, so the pulses will appear more closely, so the frequency increases. So you have this frequency of the pulse signal, pulse train, being proportional to the input current. So if you measure the frequency by measuring the number of pulses in a particular time, then we have indirect indication of what is the input current. Now similar to this, we can also have a resistance to voltage conversion. This is much simpler. So you have a standard current source, okay, or rather it's a voltage source that is with a large resistance, with a large internal resistance. Okay, so you have a voltage source which is connected to a large resistance, and that is connected to the unknown resistance here. Okay, now the voltage across this resistance is approximately equal to I times the resistance R. Okay, and this I is some reference voltage divided by R series. Now R series is much greater than this R. Okay, so just to be clear, let me draw the intended circuit. So what you have here is this current source is the same as a voltage source into RS. So this is V reference in series with RS, and RS is much greater than R. Okay, so V ref by RS plus RF, this is I, this is the same as V ref by RS. Okay, so that was the intention that we have. So in any case, what you end up with is a circuitry where the voltage across this is some constant current I, a known current I, times the resistance, unknown resistance R. Okay, so this is proportional to the resistance R, and therefore if you measure this voltage, you are indirectly measure what is the resistance R. But there is a dependence, there is an assumption that the internal resistance is much greater. And we already have circuitry, we already have op-amp based circuitry which inherently have high input impedance and low output impedance, so that can also be utilized. Okay, so you still have this constant current generator. Okay, and now if you connect a unknown resistance here, then as with the earlier case, you have the voltage here, V in is proportional to Rx, and that can be amplified appropriately with a factor of R2 by R1, and this voltage, the output voltage, is now proportional to the current Rx. Okay, so this can be used when the low resistance case, that is Rx, is much less than the input resistance of this circuitry. However, when Rx is comparable, not really approximately equal to, comparable to Rn, then this sort of circuitry is not going to be useful. So a slight modification has to be done. Okay, so in this case, you really use a low resistance here and shift the unknown resistance here. Okay, now what you have is the output is Rx by R1 times some constant input voltage. So again, your output is proportional to this, the unknown resistance, and you can go ahead and use the circuitry, use the second circuitry for high resistance case now. Okay, so with that we come to this end of this particular lecture, and you can see chapters 15 and 16 of the book by on digital instrumentation by Bowens. Okay, that is automation in voltmeters and digital multimeter circuits. Okay, and with that we come to the end. Thank you for your patience.